Hi everyone, welcome to this session on providing capacity and TCO benefits to applications using VMware's software memory tiering. This is a SNIA session and my name is Arvind Jagannath and I'm Senior Product Line Manager at VMware, responsible for the platform infrastructure. And I'm joined by my colleague Sudhir Balasubramanian, who is a Senior Staff Solution Architect for Oracle at VMware. Here is a brief agenda, and today we'll talk about motivation, and I'll also talk about memory tiering and the CXL use cases. Then Sudhir will talk about how it's applicable to Oracle, and he'll talk about optimizing Oracle workloads, and he will present a use case, and then we'll go through the key takeaways. All right, when you look at some of the VMware competencies, VMware is known for virtualization. So VMware is one of the first industry leaders for virtualization. And what does it mean for technologies like CXL? So basically what that means is you can go and make any underlying hardware change, and VMware will support that. Basically, the virtualization layer will completely hide all the hardware changes that are being made, and they will the virtualization layer at that point will just present an abstraction. Basically, it will present memory or it will present virtualized CPU, and all the applications that run on top of it can take advantage of it. Basically, the implication is that it's completely compatible with any applications you have been running for the last 3 to 5 years, for example. And you can bring those same applications and you can run those on newer hardware. And thus, it is really ideal. Virtualization is ideal for transparent memory tiering kind of use cases. VMware is also built from the ground up with resiliency in mind. So we have something called dynamic resource scheduler. It's a cluster-wide entity that helps load balance and mitigate risks. So in case there are resource management issues, DRS acts and makes sure that workloads do not face any kind of performance issues or disruptions, and they can run without any issues on that cluster. And then we have a strong ecosystem of partners. So VMware over the years has developed several partners in the IO side of things, in CPU side of things. And we have a lot of OEM vendors and even some of the application vendors. And that actually puts us in a good, strong position, because now we are able to work across the board, across this ecosystem of device vendors and OEMs, and ensure that newer hardware technologies can be supported across the board and they can be validated. So at the bottom, I show some of the example use cases that we started supporting recently, such as, we supported some innovations such as pass-through devices, where, the hardware is passed through to applications if required. We also shared things, we also did things like sharing of GPUs and assignable hardware. So things like GPU direct and support for bit fusion kind of use cases, where hardware can be disaggregated. And recently, we also supported things like smart NICs. VMware also has supported things like telco accelerators. So VMware has been big in the accelerator space as well. So next, let's go through, dive and actually take a look at what VMware has been working on over the years, and what are some of the CXL use cases that we are looking into. So VMware's big memory and disaggregation vision actually starts with CXL and tiering. CXL actually presents really good incentives in terms of supporting these newer use cases. And it actually is a perfect fit for virtualized platform like VMware, because CXL presents an opportunity to do a lot more with how virtualization plays with respect to the different hardware. So in fact, things like different types of memory that can be supported in a PCI form factor, accelerators, those can be supported using CXL. Besides, VMware is also looking into supporting different types of devices. We are starting to look into type 3 devices, and then we'll also look into potentially type 2 and even type 1 devices in the future. So what are some of the value propositions for VMware when we say that we support memory tiering? So first of all, like I mentioned before, virtualization actually completely abstracts hardware changes. With respect to memory, we also provide a single transparent memory address space. So which means that, any extra memory that is taken up by the supporting technologies like tiering can be presented as a single address space. And this requires no guest or application changes. And any operating system could be run. And basically, ESX handles all the page placements and page tracking, and it makes sure that it can transparently move pages. And that's where CXL shines, in the sense that CXL avoids any page fault type of mechanisms, which actually require pages to be explicitly moved to DRAM. So CXL can actually take that a notch higher, where it can start looking into, where VMware can start looking into some use cases where devices can directly be accessed and pages inside the devices can be accessed. DRS and vMotion are available. Like I mentioned before, DRS and vMotion help to mitigate risks. Plus, we also ensure that any new hardware infrastructure capability that we add is automatically fed into DRS, and it becomes DRS aware. VMware also has the philosophy that we ensure fairness, which means that no single VM can hog the memory or some hardware resource entirely on its own. So we ensure that there is no starvation and all VMs get equal opportunity. Our other philosophy is to ensure that minimum hardware or configuration changes are required. So anything that we build in terms of newer protocols or newer software changes, they should be available without configuration changes. We also are trying to make sure that performance is a big thing. We take into account any performance degradation and ensure that we uniformly support different types of workloads running on top of the hypervisor. And we also ensure monitoring. For example, we recently started supporting VMMR, and that can monitor both at a VM and a host level. It can monitor different types of memory, both on the bandwidth side and the latency side, and it can display those in the vCenter. Now let's take a look at some of the key use cases emerging with CXL. So across the industry, VMware has been trying to work with a variety of device vendors. And what we see is a variety of different use cases that are emerging. And the primary one is, of course, the type 3 devices with memory expansion. Basically, these memory expanders provide increased scale and capacity. They provide a flat expansion. They also help consolidate server memory. So there is no need to provision extra servers. In many cases, the same server can be made to run bigger workloads or more workloads. It can also help improve bandwidth for some bandwidth hungry applications. So we know that in some of the platforms, in some platforms at least, the bandwidth is a concern. We have limited number of memory channels, for example. CXL does provide that extra bandwidth where we are able to utilize any hogging of bandwidth that's already been done by other applications. Now, newer applications can use and take advantage of the extra bandwidth provided by CXL. There is also improvement in the core utilization. There's always a thinking that there is a core to memory imbalance. So CXL can help bridge that imbalance and ensure that cores are fully utilized. The other use cases are memory tiering, which provides lower TCO when combined with cheaper memory. Memory pooling is another use case where memory can be consolidated across a cluster. We are also looking into use cases such as memory sharing in the future, and other use cases which involve possibly accelerators, where we make use of accelerators to provide VMware specific value propositions, which can help improve ESX's performance of various features. There is also CXL switching and shared access, such as a pooled device and rack-based device that can be supported using switches and potentially be shared across multiple hosts. So this actually brings us to the next level of disaggregation and composability. Let's now look at some of the deployment options. So as I mentioned, VMware has been looking at memory expanders. So you can actually use memory expanders that can help integrate with the address space that's already provided by DRAM and provide a single address space. And this address space could be uniformly be accessed and used by the workloads running on top of the hypervisor. Then we have the tiering use case, which is about TCO reduction. So you could have a slower, inexpensive tier 2 that is connected by CXL, and that would have slightly higher latencies at lower costs, but we could actually perform active tiering within the ESX kernel that could actually make the performance near to the DRAM performance, which means that we'll actively do page placements and replacements and tier between hot and cold pages and ensure that the performance doesn't change or performance doesn't get affected. Similarly, we are looking into NVMe tier for much smaller tier ratios. So NVMe is more ubiquitous, which means that a lot of our customer base already has NVMe, and this could potentially be a solution. We are also looking into memory appliance for pooling, like I mentioned before, and we already have DRS as a clustered entity, and we are definitely looking into ways in which DRS could actually perform the function of a fabric management layer. So let's look at a quick example of how we could actually reduce total server costs. So I mentioned that there are potentially ways in which you could reduce the overall costs of DRAM. DRAM, as you all know, is very expensive, and we need to ensure that for our customers, we provide the same value without degrading the performance, and we are able to reduce some of the TCO for our customers. So on the left, you see a pure DRAM system, which is significantly higher cost. And when you combine a lower cost memory, which is much significantly lower cost and actually can help compensate for the DRAM that has been taken off, so you see a significant reduction in the cost. So in this specific case, you can see up to 36% cost reduction compared to a DRAM only system on the left. So here are some of the CapEx and OpEx improvements that we are looking into with respect to CXL. So what are the advantages? So basically, with respect to CapEx, we lower the TCO by doing DRAM substitution. And then for a lot of our customers, capacity and bandwidth is a concern. So we can help consolidate or help improve on their TCO by helping them run more workloads on the same server. And similarly, we can help with the core utilization. So a lot of the cores, in most cases, they can become underutilized because of the non-availability of memory. So by presenting more memory dynamically, you can help improve that core utilization. You can have CPU savings from doing some of the page tracking or even offloading some of the page transfers. So that's another use case that can be looked into by things like accelerators. So in terms of reducing OpEx, this is actually specifically how we are dealing with VMware specific operational improvements. So a lot of the things such as migrations can actually be operationally expensive. So VMware is definitely looking into ways in which it could reduce OpEx costs for our customers. And we are also looking into potentially reducing the failure probability. Because this is memory, anything that actually has to deal with pages such as migration or tracking memory or making memory more resilient has to do with improving the supportability for our customers and improving on the operational costs for our customers. And even things like, maintenance required, and then customers have to evacuate a full host, which is, which has terabytes of memory. So CXL can help in the sense that CXL can help track the pages, and it can help track active workloads, and it can sort of make this granular in such a way that migrations can happen much faster. There are other use cases such as memory tracking and scrubbing and proactive maintenance that can also be looked into. A lot of other offloads that are specific to VMware can also be looked into. So these are some of the future enhancements that we'll be looking into. Next, I will pass this on to my colleague, Sudhir Balasubramanian, to talk about how CXL like tiering can also help optimize Oracle workloads. Thanks a lot.
Thank you, Arvind. And moving on, let's look at some of the Oracle workload use cases here. Essentially, Arvind spoke about how VMware software memory tiering can provide capacity and TCO to business critical applications. And today we'll be looking at Oracle as a workload, Oracle as a business critical application. And let's see how VMware software memory tiering can provide capacity, TCO, and DRAM-like performance for those business critical applications to meet their SLAs, their RTOs and RPOs. So moving on to the next slide here, right? But essentially, even before we go into the setup and how we were able to extract that metrics that we would like to show in this session here, right? If we were to take a step back and look at VMware software memory tiering, and essentially Arvind did cover that to a great length, right? Some other advantages that the software memory tiering brings to our table here is VMware vSphere as a platform, right? The hypervisor as a platform that has the most awareness of the workload memory access pattern, right? We understand, or VMware vSphere understands the memory allocation, and essentially how we can control the memory allocation on demand, right? vSphere has that intelligence to manage the hot and the memory cold pages, and all of that happens transparently to workloads, right? That as compared to, let's say, if one were to go with some kind of hardware memory tiering, absolutely, yes, you could do that, but that would not have the workload or the sense of the workload, the demand for the hot and the cold memory pages as good as what VMware vSphere provides, or brings to the table here. So essentially, the software memory tiering provided by VMware can span across all memory technologies. It doesn't have to be restricted to Oracle. It can extend that to your SQL Server databases, SAP, or anything that's business critical, and can that make use of that memory transparently, right? And that can span across all memory technologies, be that DRAM, be that tier 2 memory or NVMe, or even we can extend that to CXL as well at some point of time. All right. So let's look at the lab setup that we have here before us. Essentially, what we did was we had two servers, right? Two ESXi servers, exactly the same version. So the server onto the left-hand side, that's the server that has the software memory tiering the architecture, and the server on the right-hand side is a pure DRAM mode server. And let's actually look at some of the characteristics of the server, right? So from a VMware version specific perspective, the servers are exactly the same. Both the servers had 4 sockets. Both the servers had 24 cores per socket, which means each server had 4 NUMA nodes. The only difference here is the server onto the left-hand side had 1.5 terabyte of DRAM and 3 terabyte of tier 2 memory, which means it had a total of 4.5 terabyte, which includes 1.5 TB of DRAM and 3 terabyte of tier 2 memory. Server onto the right-hand side essentially had a 1.5 terabyte of DRAM alone, right? So the software memory tiering server had that extra 3 terabyte of tier 2 memory, right? And the reason we did that is because we wanted to show that we are able to achieve, more capacity and essentially achieve TCO and provide DRAM-like performance, right? When we are able to increase, or when we are able to encompass those disparate memory technologies, right? Under one common, blanket, which essentially is the software memory tiering server or the architecture. Okay. This is a view from a NUMA perspective. So essentially, I've like I mentioned before, right? Both the servers had 4 sockets, and every socket had 24 cores. So if you look at the illustration here, you would see that the server on the left-hand side, which is the software memory tiering server, essentially has 4 sockets. Every socket has 24 cores. Every socket has 384 gigs of DRAM and 768 gigs of tier 2 memory. The server on the right-hand side is a pure DRAM mode server alone, which means it has 1.5 terabyte of DRAM in total, and that broken up among 4 NUMA nodes. So every NUMA node had 384 gigabytes of DRAM. So that's per NUMA node, per socket. Okay. What we then did was we went ahead and we created 3 virtual machines exactly the same. So essentially we created 1 virtual machine. We cloned 2 other virtual machines from this VM. So that way the version of Oracle, the version of the operating system, pretty much all the characteristics about the virtual machines are set exactly the same, right? So 2 such virtual machines on the software memory tiering server, 1 such virtual machine on the DRAM only server, right? So if you look at the left-hand side of the illustration here, right, you would see every virtual machine on the software memory tiering server had 12 vCPUs, which are the virtual CPUs of the virtual machine, and every VM has 256 gigabyte of memory, which means a virtual machine's vCPU or virtual CPUs and the virtual machine's RAM can fit very nicely and very easily within a NUMA node, right? And what we did was essentially, right, in the case of the software memory tiering server, we actually went ahead and we affinitized that virtual machine to NUMA node 0. And that's what is indicated in the bottom of the slide here, where it says NUMA node affinity. We went ahead and we set the affinity to 0, right? And we did the same thing across the board for the virtual machine sitting on the DRAM server as well, right? So it also has 12 vCPUs and 256 gigabyte of VM memory. We also made sure that we set the affinity to NUMA node 0. We did that so that we can dispel all noise, right? And we are able to run this experiment, right, in controlled environment. And that's the reason we did that, right? So that we don't have VMs spanning across NUMA node, and then you don't have that memory latency, coming across any kind of QPI link. So to avoid that, we went ahead and we did that. Okay. So looking at, or let's say moving up a level, right? Looking from an Oracle database perspective, right? We installed Oracle OEL, which is the Oracle Enterprise Linux 8.5 UEK. UEK stands for the unbreakable kernel. The Oracle version was 21.5. We made sure that we had a standalone database on all 3 virtual machines. We use Oracle ASM to provide the storage, ASM library for device persistence. We essentially made sure that all Oracle on VMware best practices that's followed, right? And from a Oracle memory perspective, right, that's what the Oracle SGA and the PGA stands for. The SGA stands for the system global area. The PGA stands for the program global area, right? We set the SGA and the PGA to 192 gigs and 30 gigs across the board, which means for all 3 virtual machines, right? And our goal of today, right, the goal for today is to run 2 software tiering memory virtual machine, which means 2 such virtual machines on the software memory tiering server, the server on the left-hand side, on 1 NUMA node, versus running one such virtual machine on the DRAM only server. And the ask of today is to see, can we double our workload performance with lower TCO, right? Are we able to double it? Are we able to get lower TCO? And of course, with adding the we're adding the tier 2 memory, we have larger capacity, right? For lower cost, much lower cost than the DRAM on the software memory tiering server. So that's the goal for today, to run two such virtual machines to see, can we double our workload performance with lower TCO? And we ran a lot of tests. Essentially, we ran a lot of tests, and I'll be going to some of the metrics here on the session here today. But even before I do that, the load generator that we chose as a workload generator that ran against these three virtual machine databases was SLOB. SLOB stands for Silly Little Oracle Benchmark, right? And essentially, it's a industry standard workload generator, right? And there's some settings that definitely I would like to call out. And the first setting is the update PCT. The update PCT stands for update percentage. So we set the update percentage to 0 because this was a read-only test. We did not want to do a write-only test. We wanted to do a read-only test because we wanted to compare the performance between software memory tiering and DRAM mode. The second parameter is the runtime, which essentially was set to 1200 seconds. So that's 20 minutes, right? So we ran a set of SLOB test against all three virtual machines in parallel, right? And of those tests, we basically collected 3 or 4 runs, and from those runs, those are the metrics that we'll be going through the session here today. So essentially, if we focus on the test results, the very first metric I would like to draw your attention to is the execute SQL per second, right? What this means, and this is a metric that every Oracle DBA and probably DBAs in the SQL land as well, they kind of have a look at, which means in a second, how many SQLs was I able to execute, which essentially translate to the number of transactions that workload is able to generate, which translates to that workload performance, which means if I'm able to run more SQLs a second, right, I'm able to run more transactions in a second, and which means my workload performance has increased, right? So if we look at run 1, essentially, if we were to take the aggregate of virtual machine 1 and virtual machine 2 on the software memory tiering server, we see it's to the tune of around 69K per second, right? As compared to, let's say, looking at the DRAM mode virtual machine, we were only able to generate 41K, right, per second. We had a second run, and on the second run, right, we again saw that the aggregate for both the virtual machines for a software memory tiering server, that was close to 69K per second. The DRAM mode virtual machine that clocked at 41K per second, right? So that's the first metric, which means from an execute SQL per second, if I'm able to increase the capacity of memory by adding more tier 2 memory, right, I'm able to run more such virtual machines. I'm able to generate a lot of SQLs, which means I'm able to run a lot more transactions. Hence, I am running a lot more workload, all for the price, or all, let's say, as compared to running one such, DRAM virtual machine. And if and this, sometimes people do have questions. And the question is, well, I could do the same thing on the DRAM mode server as well, right? I could just come up with another virtual machine, and I could do that. I mean, absolutely, you could do that, but keep in mind that the DRAM server has 4 sockets, which means 4 NUMA nodes, and every NUMA node has 384 gigs of memory, right? If you recollect, the virtual machine size or the virtual machine memory size was 256. So if we were to create 2 such virtual machines on the DRAM mode server, that would be 512 gigs of memory that would have to be consumed against 384, which means the memory is highly over provisioned here. We don't have that extra 128 to give it to those virtual machines, right? So you probably cannot do that, which means you only have 2 options. You either do that and run those workloads in a degraded fashion, or pretty much dip into your pocket, go to the market, buy more DRAM, which we all know is very expensive, right? So that's to do with the first metric. Now, if we look at the second metric, which is the logical read blocks per second, right? Because right now we are taxing logical reads. We are not taxing physical reads, right? If we look at the logical read blocks per second, the aggregate of virtual machine 1 and virtual machine 2 on the software memory tiering server, that was close to like 4.8 million a second, right? And if you look at the DRAM mode virtual machine, that was 5.4 million a second. If you look at run 2, that was close to like 5 million a second for both the virtual machines on the software memory tiering server aggregated as compared to, let's say, 5.4, right? So essentially, we were getting a lot more logical reads, right? The aggregate, and that there seemed to be a typo on the DRAM mode virtual machine. We got a lot lesser than 5.4 million in a second. So I do definitely have to correct that. But the logical read blocks per second, the aggregate was much more, right, for the software memory tiering server. Okay, now we had a look at the Oracle metrics, right? Let's now move and let's now look at the operating system metrics, right? So when as part of run 1 and as part of run 2, right? If we were to look at run 1, right? And if you look at the left-hand side of the slide, the left-hand side of the illustration here, right? Essentially, you see from a VM1 perspective, right? The CPU idle time or the idle time on the guest operating system, that was much more than what you see on the DRAM virtual machine, right? Which means I have more idle time, right? I'm able to do my work more effectively because the software memory tiering architecture of the framework kicked in for me, right? And so that's helping me provide more memory than I have on that system. So I'm able to do my work more and better in an efficient fashion. I have more idle cycles, right? If you look at VM2, that's 9.8. If you look at virtual machine 1, that's 21.2. Compare that to the DRAM virtual machine, the figure, that is 8.8. So essentially, right, you are able to get more idle cycles back, right, by running these workloads on the software memory tiering server, right? Now, if we look at run 2 as well, right, the stats are almost the same. You have an idle percentage at 10% for virtual machine 1. You have an idle CPU percentage of 16.1 for virtual machine 2 as compared to 8.8 for VM1 on the DRAM mode server. So again, these stats, these stats are basically stats that we got from running the workload in our lab. And essentially, this is what everybody knows, that, any metrics is always dependent upon a lot of parameters of a function, right? It basically depends upon the lab setup. It depends upon the kind of, the workload that you run, the kind of hardware architecture that you have, and so on and so forth. And basically, the improvements that I got in a lab may be far less than what you will see with real workloads, right? Because we used a synthetic load generator, right? And when you guys go back and look at your workloads, they are real world application workloads. They're not synthetic workload generator. So obviously, and absolutely, you guys will get a lot more benefit, right? Running the virtual machines on, software memory tiering for those real world application workloads. Again, looking at the test results here, right? We were able to see that we are able to run 2 such virtual machines on the software memory tiering server. Again, we were running it on one NUMA node, right? But keep in mind, even though the physical NUMA node or the NUMA node had 384 gigs of DRAM, it had 768 gigs of tier 2 memory, which means it had a lot more than what the DRAM server had, right? Which means I am now able to, even if I do that NUMA affinity to NUMA node 0, I am able to run 2 virtual machines as compared to running 1 such virtual machines on the DRAM server, right? So given the size of the virtual machine and the DRAM capacity constraint, right? So I was able to increase my workload performance. I was able to increase my capacity by adding tier 2 memory server. I was able to then achieve lower TCO as running just one single virtual machine on one NUMA node on the DRAM mode only server, right? Solely and only because we deployed VMware software memory tiering, the framework, the architecture, or we use the feature or the capability. So from a Oracle workload perspective, just to summarize, we got more, or the aggregate execute sequels per second. That was much better, far more improved. It was almost double. The logical blocks per read, that was almost double of what we got from a DRAM mode only server. If you look at the guest operating system statistics, right, we get more CPU idle percentage in case of the software memory tiering virtual machine, which means we get better CPU utilization, right? And so we can now use those extra CPU cycles to do some other work, right? And so there's a lot of saving from a utilization perspective. Okay. So looking at some of the key takeaways here, right? I mean, business transformation, that has been leading to larger data sets and real-time analytics that requires more performance and larger memory capacity, right? From a VMware perspective, the VMware performance results show that software tiering is ready for the next big phase, right, of the big memory evolution. Applications, they benefit from being in memory. mission critical applications like Oracle, and it doesn't have to be the Oracles of the world. It could be the SAPs, it could be the SQL servers, or even big data, or anything that is memory hungry, right? Bandwidth hungry, with us memory hungry, they can benefit from such innovations, right? And VMware software memory tiering, that will bring scale without adding any operational complexity. So software memory tiering is also ready for future technologies like CXL that essentially brings pooling and disaggregation to the table here. All right. So the second key takeaway that we would really like you guys to take away from the session essentially is pretty much all Oracle workload, white papers, whether it's blogs or white papers or collaterals, right? Best practices, deployment guides, so on and so forth, they can be found at this link here, the one-stop shop. And that's what our team, we maintain, and we create those collaterals on that link. But apart from that, that's a bit about me. And that's a bit about Arvind. But then, thank you so much. Thank you for your time, and thank you for listening to us. So please do take a moment to rate this session. Your feedback is very important to us. But with that, thank you.